All right, here we go. We're now going to move away from binomial expansion and talk about binomial theorem. This can be applied to the binomial expansion as well as a topic we're going to talk about down the road in probability. So this is one that again has multiple applications. It can take the place of expanding the way we looked at on our earlier notes, but it doesn't have to take the place of those. You can always do it that way. This is another option. So our goal is to look at the Pascal's triangle and create an equation to find any particular value. So if I wanted to just find what this particular number was, I could use an equation and figure out exactly what that value was. And instead of having to write the whole triangle out, go to the 8th row, find across where the 5th or 6th term happens to be, and what would that coefficient be, or that number, I can use a formula to do it. So we're going to kind of build that. And we're going to do it using a new function called the factorial. And it cares about the number of ways something can be arranged. And if you were able to complete the coin flipping station before this, it kind of showed you how many times and how many combinations to get a heads or a tails, if you will, matched the same numbers in terms of the Pascal's triangle as you went through the triangle. So that's kind of where this is leading. So if I have 3 students in a single file line and I want to find out how many different ways they can actually be lined up, I'm just going to do this. I'm going to call my students student 1, 2, and 3. Pretty boring names, but you know, whatever. So 1 could be in first in line followed by 2 and 3, but 1 could also be first in line followed by 3 and then 2. But 1 doesn't have to be first in line. 2 could be first in line, and 1 could be behind 2 and 3 at the end, but 2 could be in front with 3 followed by 1. And 1 and 2, they don't have to be in the front. 3 could be the head of the line followed by 1 and 2, or 3 could be in the front followed by 2 and 1. And then that's it. There's no other way to get people arranged in order in a line. So there's 1, 2, 3, 4, 5. So there are 3 students and there are 6 combos or arrangements. I don't know why that's in there. That could be done. If we want to look at 4 students in a single file line, this is a little bit more complicated, so it requires me to change my color. It could be student 1, 2, 3, and 4. 1 could be in the front, but maybe 2 is not second, but maybe 2 is second, but we'll swap 4 and 3. And then that's the only way you could have 1 followed by 2. But 1 could be followed by 3, who's followed by 2 and 4, and 1 could be followed by 3 where 4 and 2 were flipped. 1 could also be followed by 4, followed by 2 and 3, and 1 could be followed by 4 and 3 and 2. And again, that's 1, 2, 3, 4, 5, 6 ways here. And if I wanted to put 2 in front instead, there are 6 ways to do that. Very similar process as this, but 3 could have been the student in front, and I could have done a very similar process. There would have been 6 ways, and 4, even though it's number 4, could have been first in line, and there would have been 6 ways. Number 4 could have been in line. So if each of these had 6 different ways, that means I could have had 24 combinations of 4 students in line. So that's not very many students. That's a lot of different ways that could be lined up. So what if I had no students in a single file line? How many ways could that happen to be? Well, that's a weird question because I don't even have numbers 1, 2, 3, and 4. So if nobody's in line, there's only one way it could be, and that would be no one's in line. There's no other way to do it. All right, so that leads us to some general notes. So if we're kind of cruising through your notes, that was all just kind of information and background. But if I have n objects, so a minute ago my n was number of students in line, there is a formula. You may not have noticed it, but what we had when we had 3 students in line, you remember it ended up being 6 combinations. Well, that's just 3 times 2 times 1 equals 6. And we also, at one point, had 4 students in line. And when we had 4 students in line, that was 24 combinations, which is 4 times 3 times 2 times 1, because this was 6, remember? And 6 times 4, 24. And so this is the general formula. If I have n number of objects and I want to arrange them, oops, sorry, I didn't mean to cross that out. I can do it in this many ways, n times n minus 1 times n minus 2 times etc., all the way down to 2 and 1. That is the general formula, and that is the factorial function or factorial notation. So this is not just me being super excited about the letter n. It is saying n factorial, which is telling me to do this process up here. So that's something you're going to see now, and it's applicable. And again, surprisingly, like we talked about a minute ago, 0 factorial surprisingly equals 1. It doesn't equal 0. And so we're now going to apply this by asking what integer is equal to 4 factorial. We already figured this out, but it's 4 times 3 times 2 times 1, and that equals 24. Now what if I do this? I'm not allowed to divide these. 5 factorials literally 5 times 4 times 3 times 2 times 1. Eventually I'm going to stop writing that 1. 3 factorial is 3 times 2 times 1. So notice what happens when I'm dividing factorials is there's some repetition, and 3 divided by 3 is 1, 2 divided by 2 is 1, 1 divided by 1 is 1. All that's left is this. So this actually equals 20. Which leads us to time for you to try both of these. And don't worry about this, because 4 factorial is still 4 times 3 times 2 times 1, and then you're just going to also multiply that by 3 factorial, which is 3 times 2 times 1. So take a pause, try both of these, and see what you get. Pause over. These are what you should have gotten. And again, I'm going to switch to red up here, because these 5s cancel, 4s cancel, 3s cancel, 2s cancel, 1s cancel. All that's left is 6. So if they just differ by 1, interesting. And notice that these two numbers actually add up to 7. That's puzzling. What we can do is go, well, look at these guys. 4, 3, 2, 1. All cancel with 4, 3, 2, 1. So I really just have 7 times 6 times 5. Divided by 3 times 2 times 1. And again, fortunately for me, 3 times 2 times 1 actually equals 6. So I just have 7 times 5, which is 35. All right, that's your try just playing around with the factorial function. It is on your calculator, and I will show you that in a moment where that is. I just have to open my calculator, but we'll do that in a moment. So to generate binomial coefficients, and again, like I said, we'll do some other things with this later, we can use this idea of having a set number of items, and you're choosing this literally, I will say the word choose with that, boom, right there, a subset of them. So n choose r, this notation means the same thing, and so does this notation, and we're going to use this a lot. You need to recognize that there is no division line in here. This is not n divided by r. This is n choose r, so a fixed number of items, and you're particularly interested in how many ways you can organize a subset of them. That n choose r, all three of these are the same, is the n factorial, so whatever is your top number, and n is always going to be greater than or equal to r. And then the bottom is r and n minus r. And again, n is going to become our degree of expansion, so in our problem it'll be something along the lines of, if I go back to our old notation, a plus b to the n, n is our degree that we're expanding, and r is the term number minus 1. So that minus 1 is important because this, remember, there's more than one more term in a binomial expansion than the value up here. So that's going to help us with that. So let's see what's next. So now we're going to use this formula to evaluate 5 choose 2. So again, this is n and this is r. My n and my r kind of look the same, so I'm going to try to fix that. So the top of this is going to become 5 factorial over 2 factorial times, and I'm going to subtract the 2. So 5 minus 2 is 3 factorial. And I'm going to do this out longhand because I can. 5 times 4 times 3 times 2. If I had like larger numbers than 5 and 2, I may not want to do this out longhand. And we have 2 times 1, and we also have 3 times 2 times 1. So I'm going to come up here. And again, I just expanded what we did earlier. But the 3 and the 2 and the 1 cancel out. And I could just multiply 5 times 4 and get 20, and there's still a 2 on the bottom, so the answer to this would be 10. So that, not surprisingly, if I had a expansion to the 5th power, we remember our triangle, Pascal's triangle, I believe it was 1, 5, 10, 10, 5, 1. And remember, this would put me one term farther than 2, so that would put me right here. And there's my 10 right there. Oh boy. All right, it's your turn to try this. Pause it, try it, paused. All right, so if you did it out, you would have gotten 330. And again, if I'm doing this by hand, I'm coming in here and I'm canceling all sorts of stuff like, ooh, those go, these go. You know, you could, if I really was crazy, I could be like, oh, 765, 765, and then you're just multiplying smaller numbers on top. And because 4 and 2 make 8, I could cross those out, and 3 goes into 9 3 times. And so you get 110 times 3 is 330 if you're doing it by hand. But that's okay. That's how it would work. So I'm going to pull up the calculator in just a moment, and then I'll show you how to do these on the calculator. Calculator, here it is. It looks like yours. So I can do any of these in the calculator. I'm going to have you kind of pause the video again and try them, but I'm going to show you a few things. First off, if I go to math and I go over to number, sorry, I'm going to probability. That's where I'm going. And in probability, see this NCR? That is our N choose R. So if I want to do this problem 4 choose 0 or 4 choose 1, first thing I want to do is put in the 4. And actually, with the new calculator, I may not have to do it to begin with. So I'm going to actually try this with the your type of calculator. So I'm going to hit math, and I'm going to go over to probability, and I'm going to choose number 3. And again, that's what I thought. So it actually fills in, pulls up the proper notation. So you can put in 4 and then choose 0 over here and hit enter, and it will give you the answer of 1 right there. I do want you to try these with your calculator yourself. So pause it. Again, it's under math. And if you go over to probability, NCR is right there. You'll notice that underneath NCR, this is the exclamation mark. That is your factorial function. So you could also use that to find any factorial you want. So if I wanted to find like 120 factorial, oops, I did not want to put that in there. I put in 120 and I go math, because I'm not going to personally multiply 120 times 119 times 118, etc. And I come down and I choose factorial. It's going to calculate that for me. And it's an overflow because that number is too large. So that is the other reason I would not do it by myself. And I will clear that, and I will pause it, and you will try these. Okay, I'm going to reduce my calculator. I don't want it to go away because I might want it again. But hopefully you noticed something true about 4 choose 0 and 5 choose 0, that they were both 1. And again, in all of the first term in each of the rows in a Pascal's triangle was 1. And 4 choose 1 and 4 choose 5 should have both been either 4 and 5, and then things get a little bit messed up. But these should have been the coefficients of Pascal's 5th row if you did them, and these should have been for the 4th row of Pascal's triangle. So that should have worked. So we're going to zoom through because I'm almost running out of time on this video, and I want to back up a little bit and not do that. So if I want to simplify this, I can do that by writing this as n times n minus 1 times n minus 2, and it looks like it's going to be horrible, but it goes down to 2 times 1. I don't know what n is. It could be anything. If I have n plus 1, I have to go n plus 1 times n, because n is 1 less than that, times n minus 1, etc., all the way down to 2 times 1. And very quickly, I hope I recognize that all of this is the same as all of this, which means all of that cancels, and I still have a 1 up there. It doesn't go away, but I have 1 over n plus 1. And now it's your turn to take a second and pause the video. Try number 3. Video on pause. Should have been something similar, and you should have ended up with n plus 2 times n plus 1, which actually can be FOIL to n squared plus 3n plus 2. My time's up. Hope you enjoyed this. I'm going to come back with part 2 for the rest of the examples.